Welcome to EduPorm EdTech. You're watching expert chemistry lectures with Abhinav Gaur. In this lecture, we will study about rate of reaction. The rate of reaction. First of all, whenever two similar or two dissimilar species interact with each other to give a new compound, then reaction is said to occur. And in any chemical reaction, on the left hand side we write species which are called as reactant, while on the right hand side we write the species called as products. In any chemical reaction, the concentration of reactants always decrease, whereas the concentration of product always increase with respect to time. That means as time move on, the reactants decreases and the product increases. Now the rate of reaction or speed of reaction is simply defined as the rate at which the rate at which concentration of reactants decreases and concentration of product increases in any chemical reaction. What important is that these reactants must interact with each other. If they are not interacting with each other, we will say that the reactants are non-reactive. But if they are interacting with each other, then we will say that the reactants are reactive. And if the reactants are reactive, they will result in formation of product. So in such case, the rate at which the concentration of reactant decreases with respect to time and the rate at which the concentration of product increases with respect to time is called as the rate of reaction. Now, let's study the mathematical form for expressing this rate of reaction. Let's say the initial concentration of reactant was R1, while the final concentration of reactant was R2. We know that initially the reactant was high in concentration, whereas finally, or we can say at the end, the concentration of reactant decreased. So we can say that R1, that means initial concentration of reactant, is greater than the final concentration of reactant. Let's say the change in concentration is delta R. So delta R will become final concentration, that means R2, minus the initial concentration, that means R1. As R1 is greater than R2, so delta R will be negative, and this negative sign will represent the decrease in concentration with respect to time. That means as the time increases, the concentration of reactant is decreasing. Now let's say the initial concentration of product is P1 while the final concentration of product is P2. So in this case, as concentration of product increases with time, so P2 is greater than P1. Let's say the change in concentration of product is represented by delta P. So here delta P will be equal to the final concentration minus the initial concentration, and as P2 is greater than P1, so it will be positive. And here the positive sign will represent increase in concentration of the product with respect to time. Now let's say initially the time was T1, then time increased and reached T2. We know that T2 is greater than T1, so the change in time, let the change in time be delta T. Delta T will be equal to T2 minus T1. Now the rate of reaction can be expressed as R, that means rate, is equal to minus of delta R, that means change in concentration of reactant with respect to time, which is equal to plus delta P upon delta T. So we defined that the rate of reaction is equal to the rate at which the concentration of reactant decreases with time. Here the negative sign represents the decrease in concentration, or the rate at which the concentration of product increases with respect to time. And between these I am using equal to, the sign of equal to instead of the sign of plus or the sign of minus. And the reason of using this equal to sign is that the concentration of reactant decreases with respect to the increasing concentration of product. As fast as these reactants are reacting, the fast is the generation of product. So all these terms are related, and that is how we represent the rate of reaction. Now let's study the graph for this rate of reaction. First we have graph for the reactants. This is the x-axis and this is the y-axis. On x-axis we have time. On the y-axis we have concentration of reactant. I already discussed in some previous videos of electrochemistry that these square bracket represent active mass, and the meaning of active mass is that the concentration is in terms of mole per liter. So let's say the time was T1, and at time T1 the concentration of reactant was R1. The concentration of reactant was R1. So at T1, time T1, the concentration of reactant was R1. Now let's say the time increases and it reaches T2, and at time T2 the concentration of reactant was R2. And here we can see the decrease in concentration of the reactant with respect to time. That means as the time moves on, the concentration of reactant decreases. So the final concentration, that means R2, is smaller than the initial concentration, that means smaller than R1. And let me connect all the lines. This gap is the delta T, that means change in time, where delta T is equal to T2 minus T1, that means the difference between time interval. And let's join these also. So this is concentration R2 and this is concentration R1, and this represent minus of delta R, where minus of delta R is equal to R2 minus R1. And let's say this is point A and this is point B. So the rate that I'm getting through this graph is the rate between point A and point B. So it will be the average rate, and represented as R average is equal to minus of delta R upon delta T, where minus sign represent decreasing concentration of the reactant. And why it is average rate? Because it is the average rate of reaction between point A to point B. It is not the rate of any point. It is not the rate of any particular point, but it is the average rate between point A to point B. Now let's study the graph of products. This is y-axis and this is x-axis and this is the y-axis. On y-axis we have concentration of product. On the x-axis we have time. Let's say at time t1 the concentration of product was p1, and when time increased and time reached p2, the concentration increased and reached p2. So the graph will look like this. As the concentration increases with respect to time. So this is, let me draw it again. Let's draw T2 a little near. This is P2. So now this is our P2 at the time T2, and this is P1 at the time T1. So this represent delta T, that means the time change in time, where delta T is equal to T2 minus T1, and this represent plus of delta P, where plus of delta P, that means change in concentration of product, is equal to P2 minus P1. And if this is point A and this is point B, so in this case also we are getting the rate between point A and point B. So it will be the average rate, where the R average will be equal to plus delta P upon delta T, where the plus sign indicate the change in the increase in concentration of product. Now these are the average rates, because we are getting the rate between point A and point B instead of at any particular point. So these are called as the average rates. Now let's say the time interval, that means delta T, which is equal to T2 minus T1. Let's say this is nearly equal to 0. That means when the delta T tends to 0, or when delta T become negligible. So at that case, the rate is called as instantaneous rate. An instantaneous rate is defined as the rate at particular instant of time. For example, this is my graph. This is the x-axis and this is the y-axis. On the x-axis I have time. On the y-axis I again have concentration. Let's say the concentration of reactant. So for concentration of reactant, this was my graph. Now this is time t1 and this is the concentration. I have to draw this graph again to make it more applicable. Let's say this is time t1, and at time t1 the concentration is R1, and with time the concentration of reactant is decreasing. So first we have this, and now in this case T2 is not here, T2 is not here, not here, and not even here. It is just closest to T1. So in this case the delta T, that means T2 minus T1, it is negligible, it is nearly equal to 0. So at under this situation I will get the rate at a particular point, and that rate at a particular point will be called as instantaneous rate. It will be represented by R instantaneous, where R instantaneous will be equal to minus del R upon del T. So instead of delta I am using the symbol of del. So the rate at particular instant of time when the delta T tends to 0 is called as instantaneous rate, and instantaneous rate R is equal to minus dr by dt, that means decrease in concentration of reactant with respect to time, and plus dp by dt, that means increase in concentration of product with respect to time. Now I will represent a rate for given reaction. So let's say the reaction is H2 gas plus I2 gas gives 2HI gas. As we discussed, the species on the left hand side are called as reactants, and the species on the right hand side are called as products. So the rate R average can be given as the decrease in concentration of reactant 1, that means H2, with respect to time, which is equal to the decrease in concentration of reactant 2 with respect to time, which is equal to the increase in concentration of product, that means Hi, with respect to time. Now, here 2 is the stoichiometric coefficient, and whenever we represent the rate saying that 1 mole of H2 are consumed, 1 mole of I2 are consumed, and we have to find out the rate in which 1 mole of Hi are formed. So whatever is the stoichiometric coefficient, we write this stoichiometric coefficient in denominator. So it will become plus 1 by 2 delta Hi upon delta T. The stoichiometric coefficient will go in upon position. So this is how we represent the rate. Now let me reverse the reaction. For example, I have 2Hi gas. It converts into H2 gas plus I2 gas. So again in this case, this is present on the left hand side, so it is reactant. These are on the right hand side, so these are products, and the rate, the average rate, can be given as minus of 1 by 2 delta Hi upon delta T is equal to plus of delta H2 upon delta T, which is equal to plus of delta I2 upon delta T. So whatever is reactant, it will be represented by negative sign, as negative sign represent decrease in concentration. Now let me give you a journal form, and this time let me represent it for instantaneous rate. So for example, we have a reaction in which A amount of A plus B amount of B gives us C amount of C plus D amount of D. Here A, B, C and D, these are the stoichiometric coefficients. So for this case, the R instantaneous will be equal to minus 1 by A del A by del T equal to minus 1 by B of del B upon del T equal to plus 1 by C of del C by del T is equal to plus 1 by D of del D upon del T. So this is how I represent the instantaneous rate for the given reaction, and the average rate. In case of average rate, I just have to replace del by delta, that means 1 upon A delta A upon delta T equal to minus 1 upon B delta B upon delta T is equal to plus 1 upon C delta C by delta T is equal to plus 1 upon D delta D by delta T. So I hope these topics are clear. Thank you.